Today, we're diving into an idea so radical it could turn a century of physics completely on its head. It's a potential theory of everything, and it's called the Gibsonian framework. The argument that our entire universe, from the tiniest particles to the biggest galaxies, is built on one single and, honestly, surprisingly simple rule. So, let's just kick things off with a pretty wild question. What if everything you see, everything you are, what if all of it, from galaxies spiraling out in the void to the little particles buzzing inside every atom, is all just the result of one fundamental computational rule? For 100 years, physics has been kind of split into two. We've got these two absolutely incredible theories. On one hand, you have relativity, which describes the huge cosmic stage of planets and galaxies, painting it as this smooth, continuous fabric of reality. And on the other hand, you have quantum mechanics, which is our guide to the bizarre, probabilistic world of the super, super small. The big problem? They don't talk to each other. In fact, at their core, they actually contradict each other. All right, so here's our game plan for this explainer. We're going to start with physics' ultimate quest for that one single theory. Then, we'll dive into this wild idea of reality as a computer grid. We're going to see how it stacks up against some major tests, explore its claim to solve one of the biggest mysteries in physics, and then finally, we'll try to wrap our heads around the staggering implications of a computed universe. For pretty much a century now, the absolute holy grail of physics has been finding that one single set of rules, one theory that governs both the massive cosmic scale and the tiny quantum world, a theory of everything. And that's where our challenger steps into the ring. The Gibsonian framework comes along and asks something really out there. What if reality isn't a smooth, continuous canvas at all? What if it's more like a computer simulation running on a discrete grid? Okay, so what is this thing really? At its core, the idea is that space-time, matter, and energy, they aren't the fundamental building blocks. Nope. They are the outputs of a simple computational process. The universe we actually see emerges from these incredibly simple exchange rules happening on an underlying 3D grid, a grid made of tetrahedrons, which is the simplest 3D shape you can make. And I gotta say, this is a massive shift in thinking. Traditional physics just assumes reality is continuous and smooth, and that on the quantum level, things are fundamentally random. This framework says the exact opposite. Reality is discrete, it's pixelated, and everything is deterministic and computed, step by step. All right, so how on earth does this actually work? Let's get into the nitty-gritty. Think of it like a game engine for reality. The whole system is called T-transfer. So, first, imagine that space itself is just a grid of points. Let's call them S particles. Now, with every single tick of a universal clock, these points of space are constantly exchanging what are called T particles. Just think of them as little tokens of time. As long as everything is sitting still, the exchange is perfect, everything's balanced. But the moment something moves, it disrupts that beautiful exchange. It basically misses out on collecting some of its time tokens from its neighbors. And that simple act of disruption, that's what we perceive as time slowing down and mass increasing. The whole thing comes from just one simple local rule. Let's make this real. This slide shows the framework's calculation for a particle moving at 70% the speed of light. Now don't worry, we're not going to do a full math lecture here, but just focus on the core idea. Based on how fast it's going, the framework's rules say, okay, you get exactly 3 T tokens. And as you can see, that simple assignment has huge consequences. It mechanically forces the particle's internal clock to slow down and its mass to go up. Things that Einstein needed complex equations about curving spacetime to describe, this framework says is just a direct computational result of a simple token exchange. It's wild. Okay, so a new theory is cool and all, but does it actually work? Can it reproduce the results we already know for a fact are true? We're going to put the Gibsonian framework up against two of the absolute biggest phenomena in physics, one from the cosmic realm and one from the quantum. First up, the heavyweight champion, gravitational lensing. Back in 1919, observations confirmed Einstein's wild prediction that the sun's massive gravity would literally bend the path of starlight. It's a cornerstone of general relativity. So the question is, can a simple grid of tokens do the same thing? And this is where it gets really interesting. Just look at the difference in philosophy here. Look at these two equations. On the left, you've got Einstein's famous formula from general relativity, which treats gravity as this smooth, continuous curvature of spacetime. But on the right, the Gibsonian equation looks totally different, right? It's not about a continuous curve at all. It's a summation. It is literally just adding up the tiny, discrete effects of curvature tokens at each individual point on the grid. Two completely different ways of looking at the universe. So, what's the answer? Do they match? They both predict the exact same value, 1.75 arcseconds of deflection. The framework's discrete, computational mechanics perfectly reproduce the prediction of general relativity. I mean, think about what that means. A simple process of just counting tokens gets to the exact same answer as a super complex theory of curved spacetime. Test 1, passed. All right, test 1 passed with flying colors. But what about the other side of the universe, the super, super small? Let's zoom all the way down. Can this framework explain the quantum world? Its next big test is to rebuild the s orbital of a hydrogen atom. I mean, that's the simplest, most fundamental structure in all of chemistry. And this slide just brilliantly illustrates the core difference. Quantum mechanics says the electron is this fuzzy probability cloud. The Gibsonian framework says nope, the electron has a real, discrete position, and it deterministically oscillates around a stable shell. But here's the crucial part. Both models agree that the most stable position is the Bohr radius. And again, the takeaway here is just, wow, a totally deterministic model gets the same result as a probabilistic one. Test 2, passed. Okay, so it can reproduce known physics? That's incredible. But now we get to its most audacious claim yet. It's not just about explaining existing stuff, but about solving one of the deepest, most persistent mysteries in all of physics. The mystery is all about a number, roughly 137.036. It's called the fine structure constant, and it basically governs how strong the interaction between light and matter is. It's one of the most fundamental constants of our universe, but for 100 years, nobody has had a clue why it has this specific value. It's literally been called a magic number. Well, the Gibsonian framework comes along and says, hold on, it's not magic, it's just geometry. It argues the value comes from a fundamental mismatch in the universe's code, a kind of packing tax you have to pay when you try to fit tetrahedral signals, which is the language of interaction, into a cubic grid, which is the hardware for addressing. And get this, the math is ridiculously simple. It starts with a base integer, 137. That tiny decimal part, the little 0.036, it comes from a simple ratio based on the grid's geometry. It's just the number of orphan nodes that don't quite fit perfectly at the edge of a computational block, that's 709, divided by the total number of nodes in that block. And when you do that simple division, you get a number that matches the experimentally measured value to 6 decimal places, a so-called magic number derived purely from counting points in a grid. So, okay, let's just take a breath. If any of this is right, what does it actually mean? For us, for reality, the implications are just staggering. We're not just looking at a new theory here. We're looking at a fundamentally new description of reality itself. Well, it changes literally everything. It suggests we live in a computational universe where spacetime, matter, energy, all of it are just emergent properties of a simple program. It would be a truly unified theory, with all forces coming from one single mechanism. It would replace quantum randomness with step-by-step determinism. And maybe most importantly, it makes brand new predictions that we can actually go out and test. You know, the author of this framework, James Gibson, he wraps up his paper with this fantastic little nod to Carl Sagan. Sagan once famously said that if you wish to make an apple pie from scratch, you must first invent the universe. This quote, it's a quiet, confident declaration that the recipe for the universe might have just been found. And that, of course, leaves us with the ultimate mind-bending question. If our entire reality, every star, every planet, you, me, every single thought, is the output of a computation, then what exactly is the hardware it's running on?